Okay, so today I thought we'd try something a little bit different. We're going to look at a projectile that is subject to a constant thrust force. So imagine like a bottle rocket or something. Notice here, we're going to make some assumptions. We're not going to be able to analytically solve for the final trajectory or anything. We'll have to turn to computers for a little bit of the numerical analysis. But we can still get a little bit of interesting analytical insight here. So here's what we're imagining. I have some projectile, it's this little dot right here. It's launched from some angle as usual, some initial speed we'll call v naught. But in addition to the gravitational force that it feels, we're not including drag right now, it's also going to feel a thrust force that is constant magnitude. So maybe I should say constant magnitude thrust. But because it's thrust, it'll always point in the direction of the velocity. So it's not actually a constant vector. It changes direction. But the thrust force itself, the magnitude, we'll assume to be constant. And let's call that thrust force. Maybe I'll write it off to the side here. Just to make life easy, I'm going to call it eta times the weight. That way I can compare these two forces kind of easily by just thinking about eta being the factor more or less than the weight that the thrust force experiences. I could call it something else, but it'll make life a lot easier if I just write it as some fraction of the weight. Could be greater than 1. No one said it had to be less than that. So eta is a dimensionless parameter of this setup. So the way we're going to start this is, as usual, writing down Newton's laws. Okay, now I'm not going to separate this into x and y components, at least not yet, because I want to write this in terms of vectors. There are two vectors involved. We have the gravitational field vector, which is in the negative y direction. And then we have this eta mg, which is the magnitude of this force, and I got to multiply it by a direction indicating the velocity. Now I could just go ahead and put that as v hat. That's totally fine. That's the unit vector in the direction of the velocity. We'll try to do something a little better than that when we actually analyze this, but that's a good start. And then by Newton's second law, we know that this is m, and I'll write it as dv vector dt. All right, so that's our acceleration. And our goal is to just try to do as much as we can with this. Okay, so the first thing we notice is we've been clever enough to divide out our m's. That's good. Then let's write down v hat as v vector divided by the speed. That's how you make a unit vector. And I'll go ahead and write down that g is g in the negative j hat direction. Okay, so here is our vector equation a little bit simplified. And we can see that it's pretty nonlinear. This v technically has like a vx squared plus vy squared hiding in it. Then we've got the actual vectors themselves. So our hopes are low that we can do much analytically with this. Okay, so let's go ahead and write out the components of this. I'm going to use the dot notation to keep this all together. And I think I'll go ahead and just write it in terms of the v's. So what do we have? We have vx dot, that's the x component. This term does not have an x component. So there will be an eta g vx over, I'll just leave it as v right now, but remember, v is actually the square root of vx squared plus vy squared. Similarly, vy dot is going to be minus g, that's that extra term there, and actually I'll put that at the end, eta g vy over v, and then minus g. So I have a coupled first order system of differential equations that's nonlinear. Okay, what can we do with this? Well, one thing that you could do is you could non-dimensionalize this problem by redefining what t is, define some new thing, maybe call it tau, which is g times t. Now be a little careful, the units of tau are not time. It's a speed. Maybe even we should call it something like u, just so we can kind of maybe at a glance see what the dimensions are. And if we do that, then you can divide out the g's here and rewrite this as vx, maybe I'll call it prime, That's dvx du now, which is just a sort of rescaled version of time. And that will just be eta vx over v, and then vy prime will be eta vy over v minus 1. Again, you don't have to do this, but it does make the analysis just a tiny bit easier in terms of not carrying those g's around all the time. Now, as it is, there's not much we can do about this. Like I said, this is a first order, yes, but very nonlinear coupled system of differential equations. It cannot be solved in closed form. So we're going to have to turn to our computer, either with some Mathematica or some Python coding, to see what their trajectories look like and calculate anything of interest. So what we're going to do now is turn to our computer, to Mathematica, and try to calculate what the angle is that maximizes the range of this projectile in terms of this eta. And we'll see it does have a well-defined answer as long as eta is in some range.
So while we can't actually solve these equations of motion analytically, we can use some numerical calculations to maybe get a little simulation going and try to plot out the trajectories or find a maximum range numerically. So I've written here a little Mathematica code snippet. We'll go ahead and use one of those manipulate environments to have some sliders we can drag around and adjust these differential equations as we solve them. So here we can see that we're using the ND, that's numerical differential equation solver. I've written both the differential equations in second order. So this is the accelerations in the x direction and the y direction. Notice they do depend on that eta parameter, the ratio of the thrust to the gravitational force strength. The x component will have a velocity component divided by the speed. Notice that's the square root of this Pythagorean style combination of velocity components. And in the y direction, we have the same thing, except this minus 1. Remember that I'm working in those non-dimensionalized units here. So the minus 1 really represents the minus g, but we've kind of swept all those units under the rug. And then I've got my initial conditions. I'll start at the origin. And my initial velocity components, again, I've set v naught equal to 1, will be cosine theta and sine theta. And then we'll just run this for, say, 10 units of time, whatever that is. And we'll plot the result. So here's what we get when we do this out. Eta itself is the thrust parameter. I can slide it around and change how much thrust I'm adding to my projectile. And then my launch angle in radians, I can adjust here. And you notice that for a particular fixed eta, if I launch at a very shallow angle, then I'm not going to get very far, right? We're going to have gravity take over pretty quickly and drive you into the ground. And if I launch it at a very steep angle, well, thrust is going to get you pretty high in the air. But the second you turn over, thrust is going to drive you back down into the ground, so you won't go very far. That means there's some sort of intermediate angle that'll depend on this eta, this thrust, that gives you a maximal range. Notice the units here are also in units of v naught squared over g. We've kind of non-dimensionalized. And we can see that we don't really have a symmetric shape to our trajectory. It kind of looks parabolic-ish, but not exactly. We can take eta all the way down to 0, and then we really do recover our standard parabola. That's what we expect when there's no thrust at all and just gravity. And then at pi over 4, which is somewhere around 0.75 or so, we can see that we get that usual maximal range. Launch too high, you don't go as far. Launch too low, you don't go as far. So there is a maximum. And then as we turn up this eta parameter, that angle that maximizes the range will change, usually something higher than the 45-degree launch angle. We can also see that if eta gets too big, this trajectory might just never come down. After all, if eta is greater than 1, then your thrust strength, at least in the vertical direction, would be equal to or greater than gravity. And so you just might never come back down at all. You've left. So this really is only going to work for eta less than 1, unless we're also launching off to the side. So for example, if I have a really shallow launch angle, even if eta is greater than 1, I can still come back down because I'm just, gravity is beating out the thrust component in the y direction. But let's mainly deal with eta being less than 1, so that I can look over all possible angles of launch. The next thing we might want to look at is, how do we calculate that maximal range, or the angle that maximizes the range? So there's a lot of junk here. Don't worry too much about it. I had to do it in a slightly different way here. It's a little sluggish to try to update this in real time. So instead, I pre-computed a whole bunch of different launch ranges, and then we can sort of cycle through those. So basically, yes, I still have my differential equations. This time I'm stopping them when the projectile hits the ground or goes negative, instead of necessarily stopping my t at some value. And then I'm going to just sort of run through a whole bunch of launch angles 1 degree at a time. I won't do this in radians. Notice I'm going from 1 to 89 degrees. I'm not going from 0 to 90. And the reason for that is the diffie-q's break down at those two particular cases. If I launch it at 0 degrees, it immediately goes to the ground. And if I launch it at 90, the range is automatically 0 for any launch speed, or I should say any thrust. So we'll just sort of scale through these from 1 to 89 to avoid those singularities. Okay, so here's our graph. And notice that what we're graphing here is the range in units of v naught squared over g, and the launch angle, this time in degrees. And this red dot represents the maximum. Notice we have a slider where we can adjust the thrust parameter. And this red dot tells us the maximal angle and the range at that maximal angle. So if I bring this way down, of course, at 0, I expect the maximum range to be 1 in these units, and it should occur at 45 degrees, which it does, so that checks out. As I increase the thrust parameter, though, notice that my maximum range is higher than 1, and it occurs at an angle that's larger than 45 degrees. So for example, at eta equals 0.5, we can see that the angle that maximizes the range is actually closer to 60 degrees or 61 degrees, and it does go a little bit further out. And as I increase that further and further, this shifts further and further to the right. In other words, you're spending more and more time in the air if you launch more vertically. Never mind about gravity. We've got plenty of thrust to keep us high before we turn over. This bit here on the end where it looks like it abruptly stops, no, it doesn't. That's just an artifact here. At 90 degrees, this should basically plummet straight down to the theta axis vertically. That's why the slope is kind of undefined there, and so we omitted that. But this does actually go down. Same thing on the other side. This connects to 0. As we go up towards 1, we see that sort of strange behavior where, okay, I'm cutting this off at 89, where we're aiming it straight up almost, and the thrust is equal to the weight in terms of its force magnitude. You can kind of get arbitrarily high before it turns over. So that's why we didn't go up to 90. Another reason not to go up to 90. But for generic values, we do see that there is going to be some sort of maximal value that gets higher as you turn up the thrust. And the launch angle also gets higher.
Okay, one last thing that we can talk about here that is analytically possible. We can't solve for the trajectories analytically. That is just not going to happen in terms of elementary functions. But we can do a little more analysis. We can try to look for some kind of conserved quantity. Now, this is a thrust force, so we're not really going to be able to write that down as like a, or probably not going to be able to write that down as a gradient of some potential. But sometimes you can still end up with conserved quantities, even in places where it might seem like you wouldn't think of that naturally in terms of like energy, right? We know energy is not conserved here. There's an external force doing work. We're not expecting momentum to be conserved, et cetera, et cetera. But is there anything that's conserved? Maybe some weird combo. And it turns out there is here. So let's define two new variables. I'll call them Q, which is Vy over Vx. And by the way, notice that this is just the tangent of the angle that the velocity vector makes. It's changing with time. It's not just my initial launch angle. But we'll define Q. And then I'll also define P, which is 1 over Vx. Weird that we would define that, but you'll see why. Okay, the first thing I'd like to do is try looking at Q prime, the U derivative here with respect to U of this quotient. Now it's a quotient rule, so it's going to be Vx Vy prime minus Vy Vx prime all over Vx squared. But now I have expressions for Vx prime and Vy prime that I can plug in. So I'll write this as 1 over Vx squared. I'll pull that to the front. Vx times Vy prime. Well, that's going to be Vx eta Vy over V minus Vx, just distributing that, minus Vy times this. Well, that's Vy eta Vx over V. And we notice something kind of nice here. The Vx Vy terms actually cancel. And we're left with just minus Vx over Vx squared. Or, in other words, minus P. So that's kind of interesting. The derivative of Q is minus P. And in sort of the theory of canonical variables and Hamiltonian transformations, we could try to then make this into a canonical momentum position pair. I'm not actually going to do that here. It's just a nice thing to notice. What I am interested in, though, is looking at this sort of quotient rule version of Q. Because now I want to try looking at Vx prime times Vy prime in a couple different ways. First of all, I can take Vx prime and I can multiply it by Vy prime. Or I can leave the Vy prime and multiply by Vx prime. Now, because this is not a prime there. Because these are equal to each other, I can kind of subtract them in a particular suggestive pattern and move some stuff around. So what will we get? We'll get eta times, I'll keep this side kind of on the correct side. So we'll have Vx Vy prime. This will all be over V. And then I'll subtract this term over. And that is Vy Vx prime. And then I'm left on this side with just minus Vx prime. But this right here is actually very closely related to Q prime. This is just going to be eta. This is the numerator of Q prime, so it's Vx squared, moving this guy over here, Q prime over V. Okay, that's looking kind of nice. Let's recall that V is Vx squared plus Vy squared. So I could rewrite this in terms of Q by pulling the Vx out. I am assuming that everything is happening to the right here. So if anything, if Vx goes negative, maybe I should put absolute values. But I can really write this as Vx times the square root of 1 plus this ratio squared. Well, that's just 1 plus Q squared. So let's use that expression for V and plug it in under here, move a few things around and see if we can get a nice differential equation involving Q and Vx. Okay, so what I did here is I pulled out that Vx. There was a Vx squared here, so one of them canceled, and then the other one I just moved to the other side. I'm separating variables here. And notice we've done it. The left-hand side is a function only of Q, and the right-hand side is a function only of X, so I can integrate both sides. And what I'm actually going to do is I'm going to add this to the left-hand side, leaving a 0 at the end. So when we do that, the antiderivative here is probably most easily written in terms of the inverse hyperbolic sine. I'll let you go rewrite that as a log if you really want to, but I'll think of this as the arcsinch of Q. And then the right-hand side is just, well, natural log, right? With a negative sign. I'll move that over as well. And we're left with the fact that this is just equal to some constant. C, something like that. So that's kind of interesting. It tells us that this quantity right here is a constant at all times. We've found a constant of motion in this very not constant type problem. So Can we rewrite this so that it's a little more in line with the given parameters? Of course we can. Arc-cinch can be rewritten in terms of natural logs. I can then combine all of these natural logs together, maybe exponentiate a few things and get a different constant. Let me do that for you here. So arc-cinch, by the way, if you want to write it out, is natural log of q plus this square root. That's how we write it. That's also how you would get this if you didn't know about hyperbolic functions. Once I've got that natural log, the eta can move to the power. I now have a sum of logs. So the other way of saying this is that q plus this square root to the eta power times vx, all of that is equal to e to the constant, which I'll just call some other constant. And finally, if you did want to rewrite this one last time, remembering what q is, either in terms of theta, which is kind of convenient, or in terms of vx and vy, there's a lot of different ways you can write this. We end up with this relationship between, again, either the components vx and vy, kind of complicated, or maybe better in terms of v, the speed, and theta, the angle that the velocity vector makes. In that case, what would we have? We'd have q, which is just tan theta. 1 plus tangent squared is secant squared. Square root of that's going to be secant. So I have tan theta plus secant theta to the eta power. And then vx I could just rewrite as v cosine theta. All of this is a constant. So that's very interesting. It just sort of gives us a relationship between these different, the angle at which this thing is moving and its speed as a constant of motion. Nothing that looks like kinetic energy or anything, but it is a constant that comes out of this particular analysis. Feel free, if desired, to rewrite these in terms of vx's and vy's instead. I don't think it's much more illuminating, but it is interesting that we got that extra constant. So I think that's a good analysis of this problem, the projectile with constant magnitude thrust. And unfortunately, we do need to use numerical methods to calculate that range or maximize that range, or any other parameters like the flight time or the max height, anything like that. But even in this very complicated, coupled, nonlinear system, there's still occasional analytical nuggets you can get. QED.